So in this series I'll be covering all things relating to motorcycle dynamics, but not just on a surface level, but I'll be diving into the technical and engineering that goes on behind the scenes, at least as far as I'm able to. And along the way I'll be making some calculators and some tools that I'll share with you as well. So we've covered the basics of rake and trail, and I've also shared a simulation tool so you can see what happens with those parameters as your front and rear suspension compresses. At this point I've only gone as far as the directly mounted suspension because it's the perfect opportunity to discuss the leverage ratio. And for more complex suspension systems with linkage, we'll call that the linkage ratio. So what is the leverage ratio? Well, this ratio describes the relationship between the rear wheel and the RSU, specifically the amount of travel. But it also translates to the forces that the RSU is subject to, that are translated through the wheel. So let's start with taking a look at a simple, directly mounted suspension system. So to simplify this, let's assume that we have a motorcycle with a rear suspension unit installed directly at the rear wheel, and vertically. So if we have a force that would lift the rear wheel, say 10 millimeters, this force would be directly translated into the RSU, compressing it by 10 millimeters. Now this would result in 10 millimeters of spring compressions. Now the spring has an important role to provide stiffness and resistance to the forces that are being translated through the rear wheel. And the key parameter is the spring stiffness. So let's say that spring has a spring stiffness of 10 newtons per millimeter. Now we've just input 10 millimeters of travel into the rear wheel and the RSU. And that means that we've input 100 newtons of force through the wheel into the RSU. The travel is the same for each, and so is the force. This is a leverage ratio of 1:1. And in this case, if we can imagine throughout this range of travel, the amount of change that acts in the RSU compared to the amount of change that acts in the rear wheel will be the same throughout the range. So this is also a linear 1:1 ratio. Now we can change the leverage ratio by changing the position of the mountings of the RSU. So now let's move the RSU up half the length of the swing arm. We'll notice that the amount of travel it goes through is greatly reduced, and that's because the arc length that the point is mounted is much shorter. So now let's say we have 120 millimeters of rear wheel travel, and in this scenario we have 60 millimeters of travel in the RSU. That means we have a leverage ratio of 2:1. For every 2 millimeters of rear wheel travel, we'll have 1 millimeter of travel in the RSU. So here's a snippet from the updated geometry calculator, which now includes calculations for the leverage ratio. So as we increase the RSU travel, we can see that the wheel travel is also increasing. We can also see that over time, as we increase the RSU travel, the leverage ratio also decreases. This is just because of the angle of the RSU. Now what this means for the forces is that we actually see double the force, 2 times the force in the RSU. To understand this, let's consider a wrench. We apply a force at the end of the handle. This gives us a Newton meter, for example. Now if we want to counteract this force, if we want to cause this to stop, like the RSU is resisting the force that's going through the swing arm, but we are trying to stop it at half the distance, well, the torque is newtons, which is force times meter, distance. So if we halve our distance, we need to double our force in order for it to be equal. And that is the kind of relationship, that's what we're seeing in the RSU. That is why we have double the force in the RSU for a 2:1 ratio. So this covers the basic principles of leverage ratio, how it affects the travel and the forces being transmitted through the rear wheel to the RSU. In both these cases, we've looked at 1:1 and 2:1 linear leverage ratios, meaning that the leverage ratio doesn't change as it goes through that range of travel. Now when a linkage system is introduced, it really allows us to adjust and tune the way the RSU is going to move as the rear wheel passes through its range of travel. Now depending on the linkage system, this may introduce a progressive or a regressive characteristic to the linkage ratio, essentially meaning that linkage ratio could increase or decrease as we go through the range of travel. So how does that relate to what you feel as a rider? I think that's an important thing to understand. So if you have a high linkage ratio, we're going to get a lot more travel in the rear wheel than we are in the rear suspension unit, which is going to give a kind of softer feel. So that means that with a progressive linkage ratio, we're going to start with a softer suspension, and that's going to help to absorb those smaller bumps in the roads. And then as we go deeper into our range of travel, that's when it's going to get stiffer and harder to prevent us from bottoming out the suspension. So the update calculator also includes one configuration of the linkage ratio. So here, as we go through the range of travel of the rear wheel, we'll see the linkage ratio slowly decrease as a result of the progressive characteristic. We can also adjust the dimensions of the rocker linkage to see how this affects our linkage ratio. The most common part to modify is actually the dog bone, and that's going to have the greatest effect as well. So then we have regressive, which is the opposite of progressive. It's going to start out hard, then it's going to get softer as it goes through the range of travel. This is typically not found on your street bikes, but you may find it in, say, drag racing or off-road. And the reason why you might have it in drag racing is that they have a lot of force going through that's going to push all the way onto the rear end, and having that stiffer moment of travel initially is going to help keep the RSU from squatting down too much and allowing it to retain as much traction as possible. So the important takeaway here is that the suspension geometry is quite sensitive. If we make changes like installing lowering kits or we adjust the dog bone, we can really change that leverage ratio. It could be experimental for racing, or maybe it's just a lowering kit because you're short. Either way, this can really affect the suspension's performance, and especially the forces going through the RSU. We should really be careful and check if we need to install a stiffer spring in the case that we do that. So you're probably thinking this is a video about suspension, and I barely even mentioned springs. So let's get into those now. So taking our leverage and linkage ratios into consideration, we now want to select our spring. As we mentioned before, the spring's key parameter is the spring stiffness. So this is what we're going to be using to select our spring. Now what I want to consider is sag. Now this is the amount of compression that we get in the spring under, say, the static load of the bike, or the static load of the bike with the rider on. Now for each one we'll have a different percentage of travel that we're aiming for. So for instance, say there's no rider, maybe we want around 10% of full travel just from the bike's static weight. And then with the rider on top, maybe we want 30 to 35% of the maximum travel. So we have to consider the force on the wheel and it's transmitted through the RSU. So we want to consider the weight distribution on the front and the rear of the motorcycle. Typically it's around 50 to 60% on the rear wheel. Assuming we have a 200 kilo bike, it's around 120 kilos on the rear. Now assuming I'm the very heavy rider at 100 kilos, that makes me 60 kilos. And let's put all that weight on the rear. That gives us 180 kilos on the rear as with the rider, and 120 kilos with no rider. So now assuming we have a linkage ratio of 2 to 1, that means that we need to double the force that's going through the RSU. So assuming we have a maximum travel of 120 millimeters, our static sag is going to be 10%, that's 12 millimeters. And then for the static sag with rider, we're going to say 30% just for simplicity's sake. So only 36 millimeters of travel. So if we calculate this out, we're going to find that for the static sag with no rider, it's going to be a bit unreasonable. But when we look at the sag with rider, that's going to give us something a bit more realistic. So we're somewhere in the range of 95 to 100 Newton millimeters. Now, not only with the linkage system, but we can also have a progressive or regressive characteristic of the springs as well. That gives us that extra variable to affect how the suspension is going to behave. So I just want to highlight again, we really do need to be careful when making changes to our suspension system. These changes we make may seem small, but they could really have a significant effect on the suspension that we just don't realize until it's too late. If you're not sure about your suspension, but you feel that it's not right, then I recommend taking it to a professional and getting it professionally set up for you. So a lot of professionals are going to have a lot of experience and also probably access to some tools and software to help them with the selection, to make sure that they get it right. So you'll have seen throughout this video that I've already been working on some tools and calculators for this stuff. And when they're ready, I will share them through the community posts. So if you're not subscribed, subscribe and you can find the links through there. So if you're watching this and you're a professional tuner, you have any comments, critique or corrections, then please let us know, because this channel is all about learning whilst enjoying our passion in motorcycles. Now I think the next thing would be to explore rebound, preload and damping. These are all relatively new to me, but very interesting nonetheless. So if you are interested in following, and if you're interested in anything else I share on this channel, then please consider subscribing. See you on the next one.